All right, everyone, let's start. So, uh, are there any questions about the project or the midterm coming up next week? It's I think the same time, what 6:30 or something. But I'll send out an email announcing the midterm. What's that? Help session. Okay, yeah, I was thinking about that. And do you guys want to have a Friday evening help session or just make the Friday lecture as a help session? Both? Or what I was thinking is maybe have the Friday lecture as a overview or go over most of the critical concepts that we've gone and do again the same thing on Monday if you have any questions in the Monday in the lecture time so that you have the weekend to prepare or something. And then Monday evening we'll have the exam. So yeah, I'll send out an email. I think we'll have this chapter 3 on the syllabus completely. And obviously, it builds upon chapter 1 and 2, although I'm not going to ask you any direct questions from chapter 1 and 2, but you obviously need to know what are the basics of those Ritz method and finite element methods and so on. For this beams and frames, since I'm not going to assign you a homework on this beams and frames, I might just ask you one short question on this. So, but other than that, I think it's not going to be too exhaustive. So it's the the material is based on after the first midterm. So I also thought that maybe it's time to take a look at where we are sort of in the semester. And this was the syllabus that we were planning to cover. Let's take a look at some of these. So we are right about, we did all this basic review, one-dimensional problems, two-dimensional, three-dimensional problems. We left out the finite deformation and the Newton-Raphson nonlinear problems. But just I'm curious, how many of you would have liked to see some finite deformation nonlinear problems? Okay, few of you. So I guess for that we should have actually approached the chapter 2 in a little different way. But anyway, and then we also had this dynamics and time stepping. How many of you are familiar with Newmark method? Maybe if you've taken structural dynamics. So yeah, dynamics, there's not, in terms of finite elements, dynamics is not that difficult to do. All you need is an extra mass matrix, and all that machinery that you might have learned in structural dynamics will just apply straight away. So what we are doing right now is beams and frames, and after the midterm, I plan to cover plates and shells. So actually what I think is, since most of you are structural engineers, these two topics are a lot more important than chapter 2, 3, and all that, because this is really the heart of structural mechanics. So can anybody take a sort of a guess or guess about what is the difference or what are the similarities between structural mechanics and maybe solid mechanics or continuum mechanics? What makes a theory of continuum mechanics versus a theory of structural mechanics? So just a hint, beams and frames, plates and shells, these both are structural theories. And I was telling you last time, when we make a kinematic assumption, when we assume that that our body is going to deform in a certain way, and then we try to calculate back what do the equations look like, that is all structural mechanics. Underlying theory of continuum or solid mechanics is divergence of stress plus B is equal to 0. All your strain measures and all that, they are pretty much set in stone. It's the ingenuity of the structural engineer, how you think whether something is going to deform, and then try to figure out what are the equations what equations does this theory lead to. So that's why I think these two things are a lot more important, although we will not be testing you on this. But if you are going to use some beams and plates and shells in your project, then this might be of use to you. And I think we'll also have a lot more in-class problems to do over these two topics. So since we have only about 10, 12 lectures left, we will have to pretty much cover only the basics of some of these. All right, so also I think since next week is on Monday, we have the midterm. I've also invited somebody from Abacus to give a lecture on some of the advanced or nonlinear capabilities of Abacus. So that will be on next week, Friday, April 16th. Yeah. That might be tricky. Probably not. This thing I can record by myself, but that I might not be able to video record. But yeah, I guess you can make a note of that, try to attend, and I'll see if we can make some arrangements to get a video recording of that too. Anyway, so other than that, any questions from the project? How many of you have already built some small model and tried to? Very few. It can take a lot of time. So because in Abacus, what you're trying to really learn is how to create an input file. That entire Abacus CAE is you're learning how to create an input file using Abacus, and obviously it has a lot more advanced capabilities for nonlinear and contact and friction and those kinds of things. But try to keep your things simple again. So all right. So let's begin for today. Let me briefly go over what we were doing last time. We started this theory, beam theory, and we talked about what the kinematic assumptions are. So basically what I told you that if you have a beam that you're trying to analyze, the way that we have been doing till now is discretize the whole domain with finite elements. And the reason we did that was because we were trying to find the map phi. That map would take one point from the undeformed configuration to the deformed configuration. But in beam theory and all structural theories, what we say is, well, we know how this beam is going to deform a little bit already. So what we'll do is we'll assume that if we can somehow find the deformation of the center line, and we can express somehow the rotation of a cross section. We have a center line, we have a cross section. If we can somehow figure out where the centroid line will go and what is the rotation of the cross section at every value of x, then that would be a good approximation to what the deformed shape of the 3D continuum body might look like. So that was the underlying kinematic assumption, and we saw that what it looks like is this. This is the displacement of any point x. It can be represented. Right. So now note here that this x is a vector. So what we are saying is go anywhere in this domain. The displacement of that point might deform and go up to this point, and that can be expressed simply by this expression. And this expression, this x is a scalar, this x is a vector, this x is a scalar. What this x denotes is the coordinate along the centroidal line. So what we are saying is calculate to calculate where this point x goes. All we need to do is find where the centroid went and find what was the rotation of the cross section. So the rotation of the cross section is denoted by this theta vector. And again, in large deformation, large rotations, theta is not a vector, right? We talked about how large rotations, large deformations, the rotation vector is actually rotation is actually a tensor denoted by lambda, and you did a homework problem on that also. When you say that you take a body, you rotate it one way, and this way, and if you change the order of rotations, the result is different. So that's why large rotations cannot be treated as a vector. But if the rotations are small, you can treat them as a vector. And this theta is nothing but the rotation about 1, 2, and 3 axes. Um, and this cross with P. P is some vector within the cross section. So we are saying that theta cross P will take this point to its new rotated position. Once we have this center line deformation and once we have the rotated cross-section position, we know where the beam is in the final configuration. And that is basically the kinematic hypothesis. And we saw that if you plug in all that and if you take a small slice of your beam, draw the free body diagram of that slice, you have Q, which contains all the shear forces, all the axial forces. Q at x plus delta x on this face. Similarly, on the back face, you have Q at x. And moment at the back face, moment on the front face, applied tractions, applied moments. If you just write out the sum of the forces is 0, sum of the moments is 0, you will see that you will get these two equations. Sum of the forces is 0, gives you an equation that is very similar to what our equation for solid mechanics was. Now this derivative is not a div. This is a simple derivative of a scalar variable dq. Q is a shear slash axial force vector, derivative with respect to x, a scalar, and plus the applied tractions is 0. Similarly, you have one equation for moments. So this was how the beam theory assumptions work in 3 dimensions. But if you specialize them to 2 dimensions, let's take a look at what they look like. So for this case, we will consider that our beam is going to deform only in one plane. And we are going to assume that there is no deformation in x2. And actually, this assumption is okay because even if it deforms in x2, for small deformations, there is no coupling between x1, x3 and x2, x3. As long as your axis of the beam is a centroid axis and these x1, x2, x3 are the principal axes of the beam. Okay, so to simplify our rest of the derivation, we'll just consider that the beam is going to deform in this plane x1, x3. And I told you last time that the mathematical model of a beam, you have to visualize it like a centroidal line with lots of rigid cross sections. And when it deforms, it goes to this new position. And here, the angle that the normal vector to the cross section. So I don't know if you have this figure in front of you in your handout. If the normal vector of this cross section might be a little different than the tangent to the centroid. Does that make sense? So this is the cross section, this is the normal vector. The angle that this normal vector makes with the x-axis is called theta. That's the rotation of your cross section. If and the other angle is this centroidal line that it makes with the x-axis. That entire angle is called w prime. Basically, it's the derivative of your w, which is lateral displacement. So there are. I also told you about these 2 types of theories when this theta is equal to w prime. In that case, this normal vector will be aligned with the centroidal axis, and that theory does not allow for shear deformations. In general, so what kind of beams can have shear deformation? Let's say if I have a very long beam, very thin, is shear deformation important? So for long, thin beams, it is not important. But if it's a short, deep beam, it can be very stocky. in that case, the shear deformation might be very important in comparison to the bending deformation. So that's what these two theories distinguish. Um, so again, here's the same thing. What we have done is we've reduced the problem of trying to find the deformation map for each point in this domain to the problem of finding ux, wx, and theta x. Everything is a function of this one variable x. That makes it a one-dimensional theory. So we have condensed our three-dimensional solid body down to a one-dimensional line. Every beam theory is just about how this line is going to deform, how are all these cross-sections that are connected to this line are going to deform, are going to rotate. So once you have these three functions, you know the entire deformation. Okay, so let's draw the same type of a free body diagram in 2 dimensions. This is something that you should all be familiar with. You take a cross section of your beam. Actually, we should take the cross section in the deformed configuration, but since this is all small deformation, this configuration and this configuration is not that different. So we take our free body diagram in the deformed configuration, and we draw all the forces. Shear force Qx, and this is the convention that I'm using, that shear force on the positive face is pointing upwards. Is that the convention most of you use, or the opposite for shear force? Okay. And obviously the load, I'm pointing it up in the positive x1 direction. Obviously in our beams the load is pointing downwards, so you have to switch the sign if your problem is like that. So you have N, which is axial force, M is the internal bending moment, and same thing on the left side. And if you just write out the equation for sum of forces in the 3 direction, that's right here. We have N at x plus delta x right here, minus N at x right here, and there is axial applied force small nx. And you take that, multiply with delta x, which is the length of this element, you get 0. So that's the sum of the forces in the x. What does this imply now? If I take delta x tending to 0, divide it by delta x, if I divide this equation by delta x, this will become dn by dx, rate of change of axial force, internal axial force, plus applied force is equal to 0. So this is again the similar form of our div sigma plus b. We have dn over dx plus n is equal to 0. Similarly, if you write out the equation for sum of forces in the one direction, that is the vertical direction, you have q at x plus delta x minus qx plus this distributed load times the delta x. This could be varying within this thing, but when you take delta x tend to 0, that variation will not be important. So we have that. And again, if you divide this thing by delta x, take delta x tending to 0, we end up with the equation that dq dx plus applied force is equal to 0. This is another similar equation that we had before. How about the moments? Now here, if I take the moments in the x2 direction, so all the forces will create moments, all the planar forces will create moments in the x2 direction. If we sum the moments about this point O right here, what do we get? Moment at this face minus moment at this face right here. Shear force at x plus delta x times the moment arm, which is delta x, plus applied moment. You could have an applied moment which is really not that common in practice. So in most of the cases, you can actually you can neglect this term small m. But if there is applied moments, you take that delta x plus plus the moment due to this distributed force. The distributed force you can think of as as a Q times delta x. That's the total force acting at midway through delta x by 2. So that's the moment due to that. Now if I divide this entire equation by delta x and take the limit tending to 0, what do I get? So this term will obviously give me dm by dx. What do I get here? Divide by delta x cancels off, and then delta x tending to 0, I just get q. So we have q. Same thing for this. We have plus m. And how about this term? If I divide by delta x, one of them cancels off, but the other one doesn't. And when I say delta x tending to 0, this term goes to 0. So there is no moment created due to the distributed force that is acting on this beam. Question? Which one? Oh, you mean qx? Yes, so I'm neglecting, these are all functions of x. I'm just not writing the x explicitly there. So this is q of x. Q is a function of x. So this is what we get as the third equation of equilibrium for the moments. And just a shorthand notation for this, we have n prime plus n, and these are the three equations that are written out here. So now keep a note that in all this thing, we never considered any kinematic assumption. We never made any approximations. These three equations are coming from equilibrium. These are coming from statics, sum of forces and sum of moments. We are not making any assumptions in here. So, so these equations will be valid no matter what. Now, we'll plug in our kinematic assumption, and if we say that we will express our displacements in terms of the centroid line and the rotation of the cross section, then you can show that the strains can be written out like this. So this is the axial strain, which just means that how much does the beam extend? U prime. Shear is W prime minus theta, and that is the same thing. Just to show you again here, the normal to the cross section is this direction, and I just told you that this angle is theta. The tangent to the centroid line is this direction, and this angle is W prime. So the remaining angle that's between these two things, that's W prime minus theta, and that's the shear angle, gamma. That's by how much the beam is going to, that cross section is going to shear. Okay. Similarly, you can also plug in all that assumption. This assumption right here. This assumption, you can take this and plug it into the Hooke's law, the constitutive equation, and what you would get are these three relationships. That axial force is given by Young's modulus times area times axial strain. Shear force is given by G, which is the shear modulus. G is the same as your mu. We have lambda and mu in our Hooke's law. This G is the shear modulus. It is the exact same thing as mu. And then we already have, we get the familiar equation that moment is equal to EI times theta prime. So you might be familiar that EI W double prime is moment, right? But the actual exact formula for curvature, it is not W double prime, it is theta prime. This is the exact formula for curvature. If you further make the assumption that shear is 0, then you can say that when shear is 0, then W prime will be equal to theta. And when that happens, then theta prime is equal to W double prime. And then you can say that m is equal to EIW double prime. But the exact formula is for curvature is theta prime, and moment is related to curvature, which is moment is related to curvature through EI. Okay. All right. So right now, what we have derived is equations of equilibrium, strain displacement relationships, and material law. So what we should do next is talk about some boundary conditions. So actually, you can plug in all those constitutive relationships into your equilibrium equations. You will see that the governing differential equations, which is the strong form for the Timoshenko beam, comes out to be this. All I'm doing here is plugging in what is n, what is q, what is m. If you plug in that, you get these three equations. So all these three equations also represent equilibrium for axial direction, transverse, and bending. Okay. All right. So for the Timoshenko beam, which includes shear deformations, what are the boundary conditions that we commonly see? If it is fixed on the left hand, axial deformation is 0, transverse deformation W is 0, bending theta rotation is 0 at this fixed end. On the other hand, if it's a free end, then we need to specify what are the forces that might be acting at this. If there are no forces, then those will be all 0, but there is N at L, there is Q at L, and there is M at L. All these things you need to be specified. So which ones would be essential boundary conditions and which ones would be natural boundary conditions in this? Right, so these are all fixed boundary conditions. All these boundary conditions would be essential boundary conditions. And all these where you need to specify some force variable, those are all natural boundary conditions. So this was for a cantilever beam, a fixed and free beam. How about for a simply supported beam? What is the axial boundary condition? U0 is 0. I'm saying that this point cannot move. Similarly, this point cannot move up. This point cannot move in the horizontal direction. That's this. It cannot move up. That's W0 is equal to 0. How about bending? How do we write the boundary condition for simply supported beam for bending? We cannot say that the rotation will be 0 here, right? It won't be 0. But if there is an applied moment, that moment will be the boundary condition. In general, simply supported beams, we don't have an applied end moment, but we could conceivably have an additional applied moment. So let's say there is this applied moment m0. Therefore, the condition would be m at 0 is m0. And these two would be essential boundary conditions. This would be a natural boundary condition. If there is no applied moment at the end, this m0 would be 0. That's what we normally have in our analyses. So similarly, for the right hand side, what do we have? For the axial, we need to specify the axial force. It may or may not be 0, right? So we could have NL. So NL is equal to NL. And how about vertical? That transverse deformation would be 0. And the rotation would be the same condition as this at the end, at the 0 end. So W at L is 0, and similarly M at L is equal to some applied moment ML. and that applied moment might be here. So which are the essential boundary conditions on the right end? This is the essential boundary condition. Both of the they are natural boundary conditions because they deal with generalized forces. All right, so right now what we have is we have the problem of a planar beam fully formulated. We have the governing equations, we have boundary conditions. In this governing equation itself, we have substituted our strain displacement relationships and the material constitutive relationships. So what we will do now is take our equations, we'll just now apply our regular machinery for finite elements. We'll take these equations, multiply with a virtual displacement, generalized displacement, and integrate by parts and so on. So this is the first equation, the axial equation. You multiply it with a virtual axial displacement. So this is the weak form that I'm just writing out. These are the real displacement or generalized displacements. These are the virtual generalized displacements. So then take the second equation. This is your transverse equilibrium multiplied with virtual transverse displacement. This is the bending equation multiplied with virtual rotation. Add them up, and that's it. This is your definition of the weak form. So after this, what we'll do is just integrate it by parts, and if you do that, you will create one boundary term for each of those three integrals. So all we are doing is transferring this derivative, this extra derivative, over to this virtual displacement. Okay. So what we get is u bar prime, EA u bar. This multiplies with this and stays here. And the boundary term that we get is this times this evaluated at 0 at L. So hopefully this is all algebra that this actually first term you've already done in chapter 1. The new terms are these 2 and 3. So this is also actually one way to find which are the essential boundary conditions and which are the natural boundary conditions. When you integrate by parts, all these boundary terms you can immediately tell. Either this u bar needs to be 0 or this needs to be specified. Otherwise we cannot calculate what this g is. So if u bar is 0, that means it's a essential or natural. If u bar is 0, then it is an essential boundary condition. If this is specified, then it is a natural boundary condition. So similarly for all those other terms, even in this case, this derivative will come here. You have w bar times this shear term and plus the externally applied fractions. Similarly for the bending, you would take this derivative over to theta bar. You have this thing, and there is no integration by parts for this term. And what you get is basically all these three integrals with all their corresponding boundary conditions. So you can see that this term is symmetric. This term is symmetric in u bar. This term is symmetric in theta bar. But this term and this term, if you combine them, only then they will become symmetric. So just to make the entire problem symmetric, what we'll do is take out common GA w prime minus theta. So that's right here. And when you take that out common, what we'll get is w bar prime minus theta prime. So that's on, I think, on the next page, right here. And this weak form is after you do all your integration by parts, after you make your weak form symmetric. This term takes care of the axial strain energy. So essentially what we are saying here is this entire term, this is the internal virtual work. This term is the external virtual work and the boundary terms. So once again, this is the axial internal virtual work. This is the shear or transverse internal virtual work. This is the bending internal virtual work. And so this thing would allow you to set up your equation like KD minus F, right? If you substitute in all the approximations and all those things. All right, so so in order to make all those approximations, to use the Ritz method or to use the finite element method, we need to choose certain functions, right? So how do we choose those functions? Here is a question mark really, that if we make sure that this G is equal to 0 for all u bar, you choose any u bar, if this G is 0, then I can be sure that my equilibrium equations are satisfied, right? So what space of functions should this u bar belong to? Do you remember how we decided for the one-dimensional case which space it belongs to? So which space was the one-dimensional problem which space did that one-dimensional problem belong to? H10, yeah, square integrable first derivatives. And the reason that we needed square integrable first derivatives was because in our weak form, this was the one-dimensional weak form that we had obtained in chapter 1. There are derivatives to the degree 1, and therefore we need, for this integral to be well defined, this derivative squared itself needs to be well defined. That's why this needed to be H10 in that case. So what should it be here? We still have only the first order derivatives of all those quantities, whether it is u or w or theta. We still only have the maximum order of derivative is 1. So all of those functions must belong to H1 over the interval 0 to L. And this interval 0 to L is nothing but the length of the beam. So we are saying that you choose any function you want, as long as it has square integrable derivatives. Our Ritz method will work, our finite element method will work. Okay? So, and a little later on we'll see that this H1 will change actually. And since this is actually virtual displacements, we should write it as H10. This zero denotes the fact that this u bar has to be 0 at the essential boundary condition, right? All right. So just to give you an example of what this might look like, you can choose a Ritz method to solve this weak form. All you need to do is make certain approximations now. U, the axial displacement, W, transverse and rotation, we are going to approximate them with our regular polynomials. This is what we did for the Ritz method in chapter 1, where all these functions, they need to belong to this space, to this H10 space, which is just derivatives of first order continuous, square integrable, not continuous. All right, so let's take a look at this example for a cantilever beam, uniformly distributed load, length is 0 to L, boundary conditions on the left end, U0, W0, rotation 0. All the three kinematic quantities are 0 here. All the three kinematic quantities have to be specified, and they are all specified to be 0 here. This is the axial force, the shear force, and the end moment. They are all applied, all those things are 0. So if we use a polynomial approximation, we are assuming that W, the transverse displacement, is going to be a quadratic function. The rotation is going to be a linear function of x. This is a quadratic function of x, this is a linear function of x. So essentially in Ritz method also we make an assumption that our body or our beam is going to deform a certain way, and then we try to find out what is the multiple of that mode of deformation. So we have assumed this deformation, and if you plug this into your weak form, you will see that what you will get is all the virtual displacements, virtual coefficients will come out, A1 bar, A2 bar, B1 bar, they will all come out. Inside, what you will be left with is K times D minus F is equal to 0. So the exact same machinery that we have developed for 2-dimension, 3-dimension, and 1-dimension problems is going to work for this beam, for Timoshenko beams also. And if you solve this equation, you'll see that you'll get some coefficients, and this is the solution for, this is the approximate solution for lateral displacement of the cantilever beam. This is the approximate solution for the rotations at any x. And so here's also a small note that you should keep in mind. We have used a quadratic polynomial for w and 1 degree less for theta. And people have tried these things before. And what they observed was that when you actually choose your approximations in this way, that the approximation for w is 1 order higher than the approximation for theta, then you get good results. Otherwise, you get what is called locking, meaning that if you choose the same order polynomial for both w and theta, your deformation might not be equal to or close to what you should get from the exact solution. Can anybody take a guess for what might be the reason for why are we choosing w 1 order higher than theta? Because if you take a look at this equation, the transverse displacement, I told you that the shear is defined by w prime minus theta. So w prime is also a measure of rotation. Theta is also a measure of rotation. If you have different orders of polynomials for those two, the tendency for the method is to conflict with each other, and then it locks up. So, so in general, to be on the safe side, we choose the degree of polynomial for w to be 1 degree higher than theta. And then if we take the derivative w prime will be of the same order as theta. So that smooths things out. And in that case, you would get better results. So this is basically the governing equation, weak form, and all that on strain displacement and material laws for a Timoshenko beam, which includes shear. So the next topic here is a special case of this planar beam. And this theory is called the Bernoulli Euler beam theory, where we actually neglect the shear deformation. Here we say that once you give me u and w, I already know theta. So if you remember in this problem, this theta, we needed to find u, that is the axial displacement of the centroid. We needed to find w, which is the lateral displacement of the centroid line, and we needed to find theta, which is the rotation of every cross section. But in this Bernoulli Euler beam theory, what we say is you give me u and you give me w, which is the vertical displacement. So this is u. This point goes here. This is u of x, and the amount that it displaces vertically is w of x. Once you give me w of x, this theta is actually equal to w prime. So I've reduced the problem one function further. And in this case, you'll see that this cross section, that this cross section will always remain normal to the tangential line. Okay, so let's talk about this a little more. The normal to the cross section is always oriented along this line. So If you remember, this is theta and this is also W prime. So W prime is equal to theta. And in this case, shear, gamma shear is 0. So we have eliminated one more variable. We can express theta in terms of W prime now. So essentially, what we are also saying is that the beam is rigid in shear. So just to give you an example, let's say this is the beam. In this axis, it is very flexible towards bending, right? So the shear deformation is not that much. On the other end, if I try to do the same bending, then it takes a lot more effort and it's not even bending much. So this configuration is a stocky beam. In this configuration, if you apply forces, there might be shear at every cross section. That is very important. In this configuration, you can neglect shear and all the deformation is pretty much due to bending. Okay. So since we have eliminated the shear, essentially what we are saying is that the beam is rigid in shear, meaning that the two adjacent cross sections cannot slip. They will stick together. They can only open and close like this. So we have this axial equilibrium equation that is the exact same as we had before. And actually, another point to note here is that whether it is the Bernoulli Euler beam theory or the Timoshenko beam theory, in both these cases, this axial equation is completely decoupled. You can solve this equation completely independently of the other two. However, these two are coupled. W and theta are coupled through these two equations. So you would have to solve these two equations together. And the same thing is also true for the Bernoulli Euler beam. This axial equation is decoupled. You can solve that independently. The transverse and bending, you have only one equation now. We have eliminated theta, and this is the familiar equation that you should be familiar with. You have m double prime is equal to q applied forces. Okay. And once again, this m term is not really encountered much in practical scenarios. So essentially, what we are trying to solve is this. This is the bending equation that you should all always even remember and know how to derive from that small slice of beam. Okay. So there are still a couple other things. Let me just mention the boundary conditions and then we'll call it a day. So similar boundary conditions for the cantilever beam. For the axial, we are saying no axial displacement, no transverse displacement. And since bending theta is equal to W prime, the bending boundary condition is also related to W. And the right-hand side free boundary conditions, they remain the same. They are the natural boundary conditions. These are the essential boundary conditions. And similarly for simply supported beam, we have these boundary conditions. And so next time what we'll do is go over this a little more and derive the weak form for this Bernoulli Euler beam theory.